Welcome to the ProClimber podcast. In this episode, I talk to Dr. Kara Rosemeier. Kara is the director of the Passive House Academy in New Zealand and holds a PhD in architecture with a focus on building science. We talk about the importance of ventilation for good indoor air quality and learn about Kara's study into the performance of opening windows in order to achieve this.
ProClimber inspires and educates people to create healthy, durable and energy-efficient buildings to live, learn, work and play in. Well, welcome, Kara, to the ProClimber podcast. It's great to have you here.
Oh, thanks for having me.
Where are you? North of Whangarei, aren't you?
Yes, in the far north, Doubtless Bay.
Fantastic. Now, Kara, just to give an introduction to yourself, can you give us a little bit of an idea of when you were growing up, what prompted you to get into architecture?
Well, I actually started out in physiotherapy and enjoyed the work, but I did not enjoy operating in a highly commercialized health system. So I felt I could achieve a lot more if I had more time to spend with patients. But that would have quickly bankrupted my employer. So I looked for other things to do with my life. And I liked design and engineering challenges. So I eventually picked up architecture, but in hindsight, based on insufficient research, right? For starters, I thought that in 1990, everything would be computerized. And I had some fun playing around with computers. But once I started my course, I discovered that all drawings and all calculations still needed to be done manually. And so only towards the end of my bachelor degree did computers factor at university. So that was a bit unexpected. So it wasn't quite what I thought I would get. I also quickly discovered that I enjoyed the building science aspect, which thankfully was a substantial part of architecture studies in Germany at that time. A lot more than the aesthetics considerations and parts of the studies. I quite like that in building science, there are clear steps in the decision-making process, and you can get closer to the truth. So that's how I ended up studying architecture.
Oh, fantastic. And I believe before you left Germany that you were working on a project which was involving external insulation. Can you tell us a little bit about that?
Yeah, so the largest client of my consultancy in Germany was the government of a federal state. So we managed several energy efficiency incentives programs for them. So we consulted with building owners, helped them apply for grants, and also checked outcomes on site. Funnily enough, this was the first time I ever experienced in Germany someone attempting to bribe me.
Oh, my goodness. Tell us about that.
They needed to provide a certain amount of insulation to be eligible for the grant, and they had made the declaration that that's what they would put on their facade. But then we measured on site, and it turned out not to be that amount of insulation. Well, they offered me some money if I keep quiet about this, which I didn't.
I could have guessed that, Kara, having known you for a while. So that project, sort of moving over towards today's topic, was there any consideration for ventilation in those buildings?
No, so this program was a building envelope retrofit scheme where we had about 3,500 projects on the books when I left for Aotearoa. But we also managed programs for new buildings, boiler replacement, solar thermal for a while. But these were shorter-lived programs. And in addition, we were certified consultants for other retrofit and new building quality assurance programs, where consultants for the first passive house projects in the region, and did blower door tests, etc. So for the low energy and passive house projects we worked on, we had external services engineers involved. So while ventilation systems factored in the projects that I worked on, I was not responsible for that side of the projects.
So what then prompted your move over to New Zealand, Kara?
In 2001, which was a bit of a scary time to travel because it was just after 9/11. We did a 9-month tour around the world with the aim of finding a new place to live, because it was one of the drivers was where we lived in Germany. We had 265 days of rain or snow per year.
Wow.
Which gets a bit depressing. So we stayed in a few places for longer periods of times, and then decided that New Zealand was where we would like to spend the rest of our lives, closely followed by Canada. But climate-wise, weather-wise, New Zealand stayed on top, and so we applied for residency.
Nice. And what was your experience of housing in New Zealand when you arrived here?
Oh, just as everyone else, just as well. Speaking of Canada, so some friends from Canada from very cold places said, well, the coldest they've ever been was in a house in Auckland. And that was a similar experience we had in our rental in Auckland. And it was also the first time where I was able to harvest mushrooms directly from the floorboards in our corridor. So, yeah.
Hopefully you didn't feed those to your guests, Kara.
No.
I understand that you then went on to study philosophy, was it? And your PhD involved reviewing the effectiveness of ventilation in New Zealand using windows. Was this an interesting project for you?
Yeah, no. So as for philosophy, I have a collection of degrees, but I did not study philosophy. So the PhD or doctor in philosophy does not mean you studied philosophy, but philosophy is rather used in its ancient Greek meaning as lover of wisdom or knowledge. So my PhD is in architecture with a focus on building science. So, yeah.
Thank you for clarifying that.
So for the thesis, I was looking at the role of ventilation for healthy and comfortable houses in New Zealand and juxtaposing ventilation strategies and outcomes for health and comfort. So I started out with modeling ventilation strategies for the National Model House. It's a building that the quantity surveyors use as a model for quantity surveying exercises, and which was meant to represent. And well, at the time, it's a bit small for typical houses nowadays, but at the time it was viewed as a typical New Zealand house. Then moved on to monitor infiltration, air change rates, and indoor air contaminants of 15 houses, 3 climate zones in New Zealand, but all those houses were new build, but without a whole house mechanical ventilation system. So I basically calibrated my model, right? So I checked that what am I getting empirically, what am I getting in real houses, and does that confirm or refute what I modeled?
What was the outcome? Were they achieving the desired number of air changes in the building to make it comfortable and healthy?
There was a wide variety of air change rates. And so one outcome was sort of confirming previous research by a number of people. So there's this rule of thumb that from a blower door test result, you can assume air change rates, or you can assume rate infiltration at normal pressure differentials. And there was absolutely no correlation between measured air change rates and the blower door results for my houses, right? So some of the tightest houses, well, none of them was particularly airtight. So I think 3.2 was the tightest I had from memory. But some of the tightest houses had the largest air change rates, and the air leaky houses had very little purposeful air change going on. So that was the first thing to discover. Then the air quality was okay for two very large houses that were lived in by one or two people. In one case, it was lived in by someone who said, well, I'm actually spending most of my time with my grandkids and not really home. So the air quality in those houses was okay. But all the other houses without whole house ventilation systems, the air quality really wasn't great most of the time. Yeah. So the effectiveness of the air change without whole house mechanical ventilation was not reliable and wasn't great.
So do you know where they came with this 5%, is it, of openable window space? Do you know where that number was gained from?
You mean the 5% that according to the building code, that if you have 5% openable, I have no idea. I can't base this on anything in the literature. And also, well, openable doesn't mean someone actually opens and closes those openings again, right? It's there, but it doesn't really help if you're not operating this. And in fact, so I had one house in Mangere in Auckland where I recorded quite high CO2 concentrations during the nighttime in the master bedroom. And those people were making the case, and credibly the case, that they always leave their bedroom window ajar overnight. Yeah. But despite this, I had these recordings, and typically I had more than one instrument recording in parallel because there were a couple of instruments that could record more than one contaminant. So I could confirm that this was in fact the reading. And there are three potential drivers for air exchange. There's stack or buoyancy. Yeah. For that, you need a marked gradient of temperature or height. So for low-rise building in a temperate climate, you can't rely on stack as a driver for air exchange. And that was basically the case there. So if this bar mechanical pressurization, this only leaves wind as a potential driver. So even if you leave your window open, you don't have stack, you don't have wind, you don't have mechanical pressurization, very little air will be exchanged. So that's the problem. If you don't have mechanical pressurization, then in low-rise buildings in a temperate climate, the answer, my friend, is blowing in the wind. Yeah? And so as a sailor, I would really like to be able to command the wind, but it does what it wants.
So what about extract fans, Kara, in the bathrooms and kitchens? Do they do much good?
The other problem that you have with ventilation is you really want this to be continuous, because if it's not continuous, that means that in between your ventilation events, in the intervals, indoor air contaminants build up quite quickly. So the extract fans, if they are operated continuously depressurizing the building, and then you have other openings designed to let in makeup air, that can be a cheap and cheerful strategy of getting reasonably good outcomes. The problem that still remains with this strategy is the air you get in is cold air, so comfort isn't great. And there's still also a correlation, the relationship with wind. So the intake, depending on where the wind's coming from, might not always really function as an air intake. It might just be where air is escaping. Yeah, if you're on the leeward side of the building, for example, when there's something that draws air out on that facade, it might not be the depressurization of the fans might not be enough to overcome that. So it's not perfect, but it's also, well, the incoming air can't be filtered. You can't recover any heat from outgoing air that way, but it's at least a far better safeguard for indoor air quality than relying on the wind.
Now, Kara, we're being bombarded by adverts, especially at this time of the year, from all sorts of companies, HRV, DVS, etc. Surely they're going to solve our problems?
Yeah, we are one of the few countries in the world where surplus pressure ventilation systems are being used. And England was one of the few, but has now prohibited their use. So to my surprise, what my modeling showed was that they actually could work, but only with a very airtight building envelope and with the provision of exit terminals, preferably in kitchen and bathrooms, where the warm, moist air is pushed out again. But without these provisions, we just have to ask ourselves, where's the air going? It has no choice but to work its way into the building fabric, where in winter it's likely to meet a cold layer somewhere on its way to the outdoors. And we all know what happens when warm, moist air meets a surface that is cold, right? So, but yeah, with an airtight building envelope and with exit terminals, you could get directed airflow going and you could get good outcomes for indoor air quality. But that's not how these systems are typically installed, is it?
No, for sure. And you were talking about air tightness. Where should the air tightness layer be installed to work correctly, Kara?
Depends on the climate you're in. So if you're in a climate where you need any heating, it should be internally of your insulation layer. But if you're in the tropics and cool your interior, it might be better placed on the exterior of your insulation layer. So the purpose, as you well know, is to keep warm, moist air out of the insulation, right? And for that reason, it needs to be on the side of the warm, moist air.
Great. So we've talked a lot about the problems, but what is the answer to solve these problems, Kara?
What is the answer to solve these problems? Well, if you're in a high-rise building in Helsinki, the answer might be stack or buoyancy, right? Because then you have a reliable driver. But when you're not in a high-rise in a cold climate, then the only reliable means to affect an air exchange is mechanical pressurization. Yeah? So the cheap and cheerful method that we talked about that works, and that is well used overseas, is having a continuous extract fan that is possibly ducted to the wet rooms, to kitchen and bathrooms, permanently extracts there, and then you'll have makeup air for your bedrooms and living rooms. That is an option, but if you want maximum comfort and reduce your ventilation heat loss significantly, then you're really looking for a balanced heat recovery ventilation system.
Great. Can you give us a little bit of a description of how that system would be put together?
Yeah, so with the high efficiency systems, as we use them in certified passive houses, there are two fans at work. So one is supplying fresh outdoor air directly to the living and bedrooms, and one is extracting stale air from the kitchen and bathroom areas. On its way to the outside, the stale air then donates most of the warmth to the incoming air. In very efficient heat exchangers, incoming and outgoing air are separated only by a very thin membrane. These days, it's more likely to be a polymer than aluminium for a number of reasons. But if you cut through a heat exchanger, you'll see a honeycomb structure with a very large surface area, and that allows heat to be exchanged, but not the contaminants. So the membrane separates the airways. These systems are thermally a lot more efficient than the most efficient heat pump, right? So per kilowatt hour electrical energy invested, you can get out more than 10 kilowatts of warmth, even more than that in colder climates. So the measured ratio for a project in Germany with 32 households was on average 16.5 units of warmth per kilowatt hour electricity invested. Yeah. So if a very good heat pump, I know the brochures claim you can get 5 COP5 with air-to-air source heat pumps, but that's unrealistic. Realistically, you might expect 3 kilowatt hours heat out for 1 kilowatt hour electricity invested. With heat recovery ventilation systems, you get triple and quadruple that. Yeah. So it's a very, very cost-effective way of ventilating. Yeah. So this is all the side effects. So the main purpose of the system obviously is to keep you healthy and to keep your house well ventilated. But as a side effect, you get huge energy savings and you get huge gains in comfort, because then rather than outdoor air being supplied to you on the inside, you get pre-warmed air supplied to you on the inside all the time.
So, Kara, talking about those contaminants, what are the major contaminants that we're talking about that we want to remove?
That really depends on the location and the usage indoors. So there could be combustion fumes, right? But if you're all electrical on your interior, then that can pretty much be ruled out, so that you probably won't have any nitrous oxides, for example, if you're not burning gas. You will have very little particles also if you're not burning wood, right? There could still be a few particles from cooking events that if you're lighting candles or incense sticks or something like that, then that will also increase the particle load. And in some regions, actually, the main concern is radon. Fortunately for us in New Zealand, there are very few pockets in the country where radon is a problem. Otherwise, overseas, radon is a major problem, as after smoking, it's the second highest chance of getting lung cancer, right? Radon exposure. So we're quite lucky that we don't have that many places where radon is an issue. So volatile organics could also be a problem. Formaldehyde, for example, if you have furniture or any other surfaces that release formaldehyde. So, but one contaminant that you can't really avoid indoors is CO2, right? Because, as long as any creature is living inside your building, you're releasing just CO2 by breathing out. Yeah. And body odors could also be a problem for indoor air quality when things get a bit stuffy. But CO2 is probably the easiest of all of them to measure and typically quite well correlated with concentrations of other gases, indoor air contaminants, right? So particles, not so much, but other gases in indoor air are quite well captured if you know your CO2 concentration. That also makes it possible, knowing that, to just tailor your ventilation volumes, right? So if you have a CO2 sensor and measure CO2 concentrations as an indicator of everything else going on in your ear, you can adjust your ventilation. If you have mechanical ventilation, if you have windows, you can't do this. If you have mechanical ventilation, you can adjust your ventilation rates accordingly to keep CO2 concentrations within limits.
And when you install these systems, Kara, is it quite important as to where you position the vents?
Where you position the vents as in the outlets?
Yeah, where would you have inlets and outlets, and where would you put them in a room?
So you should, for your inlets, they should be somewhere where it's unobstructed. So that's the reason why I don't recommend air outlets in the floor or at floor height, right? So that has been done occasionally, but I would not recommend this, because then you're pretty restricted in moving your furniture, etc., and could also be a comfort problem. So you want them somewhere where the air can be released unobstructed into the room, and also somewhere where people are not directly get blown at with the air, because even if it's pre-warmed air, it's still slightly colder than indoor air, unless you're conditioning the air. So somewhere high up in the wall or in the ceiling would be a good place.
I hear a lot of talk about the combination of ventilation with heating and cooling. What are your thoughts on the effectiveness of that?
Yeah, so heating, yes, it's if your occupancy ratio is in Goldilocks range, if you're 30 to 45 square meters per person, then it's possible to cover all your heating demands with the ventilation system. There are a few caveats to work through with using the ventilation system, having that doubling as your central heating system. But if it does work, it's a very cost-effective way of getting central heating, right? Cooling should not be integrated with this system, as that adds too much complexity and potential for failure. So there's always condensation that you need to deal with. And yeah, so cooling I would not integrate with a ventilation system.
Now, Kara, we've talked about these systems going into passive houses, but what about our traditional houses that are being built, or even older homes? What are the considerations around those areas?
For a ventilation system to work as designed, we need the building envelope to be reasonably airtight, right? So try to get directed airflow through a sieve. That just won't work. Also, if you want efficient heat recovery, then you cannot have a large portion of air bypassing the heat exchanger. So there's no possibility for recovering heat that leaks in and out of the building or goes through a window for that matter. We also cannot possibly control the quality of air that leaks into the building. So there might be some arbitrary filtration happening when it moves through the building fabric, but no purposeful filtration. So we get in most of the pollutants in outdoor air, and maybe some that are joining them on the way through the fabric. That being said, it's so the installing a heat recovery ventilation system in an air leaky existing building will not have the good heat recovery efficiency rates, will not have all the comfort benefits, and but it still brings continuously fresh air into your enclosure, which is the main purpose of a ventilation system. So from a health perspective, it's still a good idea. Economically, it might not stack up as good as it would be in an airtight building.
Awesome. Yeah, well, I must say I've got a system installed in an old sort of 1960s brick and tile, which is pretty air leaky, but I'm still seeing fantastic results. I mean, the other morning I had 5 degrees coming in, and it was preheating the air up to 13 degrees, running on 25 watts of electricity. So I was pretty amazed at that level of efficiency.
Hey, maybe you should talk to someone who knows about air tightness and getting your bungalow up to scratch.
No, there's a lot of work still to be done. Oh, fantastic, Kara. Well, I really appreciate your time today, and it's been great to catch up.
Sharing knowledge is at the heart of our strategy to make buildings better for everyone. Sign up for our podcasts to learn more about creating healthy living conditions by protecting building structures from external and internal moisture damage. Thanks for listening. Looking forward to having you with us next time.